Hello everyone, welcome to Algebra 2B Live, week 3, going over variation and graphs of rational functions. So for week 3, we're working our way through our textbook, we're working our way through paper pencil problems and the quiz. Please let me know if you have any questions as you're going over these assignments. Definitely use this video as a resource. Here's our objectives for week 3. We're going to be using equations, tables, and graphs and dealing a little bit with variation, learning about direct variation, learning about inverse variation, and joint variation. We'll talk about what each of these means and how to represent these ideas of variation. And lastly, we're going to start looking at this idea of rational functions, a new class of functions. We're going to spend the next couple weeks after this working more with rational functions, but we're going to start looking at graphs, tables, and equations of this new class of function and talk about what they are. Okay. Here we go. You guys ready? Variation. So variation refers to how variables, again you got variation going on, how variables interact with each other in a relationship. We have three different kinds of variation that we use in mathematics. Direct variation is a direct relationship between two variables. We got x and y, two variables. And it's direct because when one variable increases, the other increases. They directly impact. When x decreases, y decreases. So it's direct variation. There's also inverse variation. It's the opposite. You have two variables, and when one increases, the other decreases. Vice versa, when x decreases, y increases. So they have an inverse relationship with each other, an opposite effect. Finally, there is joint variation, where we have two different variables, x and y, that affect a third variable, z. So we're going to look at different examples, talk about different variations, set up equations, and help you guys understand what's going on. So here we go, direct variation. Let's start with this one first. I'm going to switch to blue, because I like blue for this one. So all direct variation equations, remember x and y, my two variables, directly affect each other. They're in this form, y equals k times x. You've probably already done some with direct variation because we usually do a lot of direct variation before we start working with linear equations. And I remember even direct variation comes up typically in 7th and 8th grade as well. So direct variation, it's y equals some value k times x. And the key, if you're working with direct variation, is you want to figure out, well, what is that constant k? X and y directly change their variables. As x gets bigger, y gets bigger. As x gets smaller, y gets smaller, but k stays the same. It's constant. So let's take this problem here. Y varies directly as x. So we're working with a direct variation equation in this form. If y equals 18 when x equals 5, well then what is the value for y when x is 7? So this is a really common direct variation equation. Let's go through this one and we'll figure out, we need to find what is the value for y at this particular x value. Well, first we need to figure out what our constant is. So let's use 18 and use 5 when x equals 5, y equals 18. Let's put it into our direct variation equation. So y is 18 is equal to some value k, I don't know what it is, times 5. That's my x value. Let's solve for k by dividing both sides by 5. And we can see that k, my constant, has to equal 5 goes in 18 3 times, with the remainder of 3/5 is the same as 3.6. So k equals 3.6. There's my constant of variation. So this direct variation equation then is y equals 3.6 times whatever x is. That's my direct variation relationship or my equation. So now we can put anything in for x and find y. I can put stuff in for y and find x, but I'm going to base it off this equation. We could graph it, we can make a table, we could find other values. We can do all sorts of stuff once we have an equation. But we're asked to find what is the value for y when x is 7. So let's take that 7 and put it in for x and find y. So y equals 3.6 times Instead of x, now it's times 7 because I want to know what is y when x is 7. So let's get my calculator, and I need to figure out 3.6 times 7, which is 25.2. There we go. And if you think about it, we also have 2 points. So I know on my direct variation equation, when x is 5, y is 18. That's 1 point on the graph. Now we just found another one. When x is 7, we found out that y is 25.2. That's going to be another point on my graph. All right, there's a direct variation example. Let's take a look at inverse variation. This is the opposite. Remember, as x increases, y decreases. And flip-flop, the same thing. All inverse variation equations are in this form. Y equals some constant divided by x. You can quickly see how when x gets bigger, the fraction, some value k over x, it turns into a smaller fraction, so y gets smaller. But let's again take this example. Let's figure out what our constant is and then figure out what the equation is and solve this problem. So here we go. Y varies inversely as x. Now we're using different words for an inverse relationship. If y equals 8 when x equals 15, what is the value for y when x equals 4? Let's use our inverse variation equation. I know y is 8 when x is 15, so I have some value k divided by 15, and that equals 8. Well, to solve for it, I need to multiply both sides with 15, and k is going to equal 8 times 15. 8 times 10 is, that's going to be 120. So there is my constant of variation right there. And so the equation, my inverse equation, is y is going to equal whatever 120 divided by x is. As x gets bigger, y gets smaller. As x gets smaller, y gets bigger. But I need to find out what y is when x is 4. So let's put 4 in for x. 120 divided by 4 is going to equal y. 120 divided by 4 is 30. So there's my value. Y has to equal 30. And we have a couple points on this graph too. For my inverse graph, we know that if x is 15, y is 8. And we also know that if x is 4, y is 30. And look at that. You can see from 15 to 4, x got smaller. When it got smaller, my y values got bigger. It went from 8 to 30. So there's an inverse relationship. The inverse is actually a precursor. It's a little bit about what we're going to do with all these rational expressions that we're going to do this week, next week, and the following week. All right, finally, let's do some joint variation. All joint variation equations are in the form z equals kxy. Look at all those letters. We love them. Again, we want to find our constant is k. X, y, and z are all variables and will fluctuate. So here we go. Z varies jointly with x and y. If x equals 2, y equals 3, and z equals 4, write the variation equation and find z when x is negative 6 and y is 2. Okay, let's again, just like the others, substitute things in and solve for what the constant is. So we know z is 4. When we have k times x, which is 2, times y, which is 3. So I'm putting in all these things, and we're going to solve for k. 2 times 3 is 6. So that's 6 times k on the right equals 4. If I divide both sides by 6, k equals 4/6, which reduces down to 2/3. Okay, we got our variation. We got our constant now. Now I can write an equation. So z is going to vary by 2/3 times x and y. And again, we can change x and y around to find z and do all sorts of good stuff now that we got the equation. So now we need to find z when x is negative 6 and y is 2. So z is going to equal 2/3 times negative 6 times 2. And that's going to equal 2/3 times 6 is going to be negative 4. Negative 4 times 2 is negative 8. So there we go. Z equals negative 8. Okay, let's do a variation problem. So variation problems often involve looking for those keywords, inverse, direct, or joint, putting things in the right spots, and trying to figure out the relationship. So here we go. 20 volunteers can wash 100 cars in 2.5 hours. Find the constant of variation and find out how many cars 30 volunteers can wash in 3 hours. Now you may think, whoa, where do I get started on this? I have no sense of putting this together. Well, we have volunteers. That seems to be changing, so we need a variable for volunteers. We have number of cars washed. That's changing because we went from 100 cars. Now we're trying to find out how many other cars. So let's do C for cars. And we also have hours, right? That seems to be changing. So hours, let's let H. So we got 3 variables, V, C, and H, going on that are changing in this problem. Now, with variables, let's look at which variables affect others. So I would say the cars washed is dependent, right? It's dependent on how much time I'm washing cars and how many people are washing cars. The more people, the more hours, I'm going to wash more cars. So the cars washed is dependent on the number of volunteers, so that's an independent variable, and the number of hours, that's independent. And if I put this together now, I'm going to say the cars washed is equal to some value, I don't know, it's my constant, multiplied by how many volunteers, multiplied by how many hours. This is a joint variation problem because there are 3 variables going on. 2 of the variables affect the other third variable. All right, let's start breaking down now into some math. I've got a bunch of numbers, and let's start putting things in. I know that I can wash 100 cars, that's 100 in for C, in 2.5 hours, that goes in for H, with 20 volunteers. So I'm going to put 20 in for V. And the only thing I don't know is what is the constant. Find the constant and then figure out, well, if we have 30 volunteers, how many can they wash in 3 hours? All right, well, let's start with this. I know I can do 100 cars with 20 people in 2.5 hours. So let's solve for K. 20 times 2.5 is 50, so it's going to be 50 times K equals 100. And this is pretty easy to see that if I divide both sides by 50, my constant has to equal 2. So there we go. We now know the constant in this relationship. The cars I wash are going to equal 2 times the number of volunteers times the number of hours. Now we can look at the next example. If I have 30 volunteers in 3 hours, let's figure out how many cars I can wash. Cars equals 2 times 30 volunteers in 3 hours. 3 times 30 is 90. 90 times 2, that's going to be 180. So I can wash 180 cars. So again, what's helpful is look at your variables and the problem you have. Think of how many things are changing. Be very intentional about what your variables are, and that can help you get to the right variation and then work out the problem from there. All right, so variation was fun. That's going to be the first few sections in your text for week 3. And the last one gets into rational functions. It's a whole new class of functions. Let's review. We've looked at, in this class so far, we did a little bit of linear, like the first week or two. We did some quadratic for a couple weeks. We did some polynomial. We loved polynomial equations, functions. We did a couple weeks of radical functions. We did a couple weeks of exponential and logarithmic functions. Now we get to do a little bit with rational functions. What is a rational function? Well, rational function is any function that has a polynomial for the numerator of a fraction and a polynomial in the denominator. Just in case you're not sure what that means, here's some examples. So f of x equals 1 divided by x, g of x equals 5 divided by 8 minus x, 3x over 5x plus 3, 2x minus 5 over x squared minus 5x minus 24. You can see that some of them are simple and some of them are complicated. But the idea is we have a fraction with a polynomial in the numerator and in the denominator. It could be a really simple polynomial, like a constant of 1 or a constant of 5. Or it could be a complex trinomial and binomial in the numerators and denominators. Either way, we're going to have to draw upon a lot of what we know about factoring and about working with polynomials. So let's take a look at this basic function. We're going to look at f of x equals a divided by x minus h plus k. And again, we like to get a sense of translation of functions. So a rational function, the parent, if I take the very most basic rational function, it's f of x equals 1 divided by x. And what we're going to see is what happens when I multiply by a on the top. What happens when I apply this plus k. And what happens when I apply this minus h. And you probably already know that k is going to be your vertical shift, your vertical translation. It's going to move it up or down. We probably already know that h is going to move it horizontally. Horizontal shift, we can move it right or left. And a is kind of like your slope. It's your magnitude or multiplier. It's going to make things grow faster or smaller. All right, so let's pull up our Desmos calculator, do this function, and kind of see what trends and patterns we notice. All right, here we are, you lucky people. So I've got our function that we looked at. I made a as 1 to start with, and I have 0 and 0 for h and k, so there's no shifts horizontally or vertically. So this is our parent function. But I just wanted you to get a sense of what we have going on when we deal with rational functions. This is a weird looking deal, right? It's kind of like a little x sort of thing or a little star. This is what we call a hyperbola. So it comes at it this way and then it kind of goes straight down. It's not even connected and then it starts right back up again and goes out this way. What we need to look for and we need to be careful about are both horizontal asymptotes and vertical asymptotes at the same time. All right, so notice if I don't do anything, this function does kind of have a center right at 0, 0. 0, 0, and there's a point. So it kind of is sort of like a parabola this way and a parabola that way around this point 0, 0. And then right now we have a, let's see, oops, at 0. There's my vertical asymptote at x equals 0. And I have a horizontal asymptote. Let me change the color. I want to make that green. All right, so there's my vertical and my horizontal asymptotes. All right, let's first shift h around, right? Let's move it right or left. So if I make h 1, we shifted the whole thing to the right one, right? Notice my horizontal asymptote is still the same, but now my vertical asymptote also needs to shift by 1 to kind of match what's going on. If I make h2, it shifts my vertical asymptote again over by 2. Okay, if I move k up or down, that's my vertical shift. So let's make k -1. And you can see now I need to adjust my my horizontal asymptote down by 1 to match what changed. So h and k shifted horizontally and vertically, but they also indicate where your asymptotes fall. Finally, let's look at let's look at what happens when I change my value for a. Again, it doesn't do anything to the asymptotes. If I make a bigger, it just seems to kind of grow faster and get farther apart that way. If I make a negative, the whole thing flip-flops. So it's a reflection around itself. All right, let's go back to our PowerPoint and summarize some of what we've seen. So when we're dealing with rational functions, we deal with a simple one like this, it's called a hyperbola, similar to a parabola, but hyperbola. We have horizontal asymptotes at whatever our vertical shift is for k, and then we also have vertical asymptotes at x equals h. The point h and k is going to indicate where the center of the asymptotes meet. The domain is all real numbers except for any values that make the denominator 0. That's when it's undefined, right? You can't divide by 0. So if I have x minus h, if that turns into 0, then it's undefined. That's not part of the domain. The range is all real numbers except for that of the vertical asymptote. All right, so we got trickiness. We have to be very careful when finding the domain. We have to be very careful when finding the range. We have to think about asymptotes both horizontally and vertically. Let's dig into a good problem here. Graph the following rational function, and then we're going to find all the asymptotes, and then we're going to find the domain, find the range, and then we're going to find the x and y intercepts. So the first thing I'm going to do is I'm going to go use my Desmos calculator and let's graph it and see what we have going on. Then we'll come back and we'll talk about domain and range and the intercepts. All right, here we are. We got my function in here. I've got my graph. Let's kind of play around with some of the things we looked at. So we knew the y value, the y-intercept. We put 0 in for x, and we got negative 1 1/3. And yes, that matches up with my y-intercept on my graph. Negative 1.333 is the same as negative 1 1/3. Our horizontal asymptote, it got really close to 1/2. You can kind of see it gets closer to 1/2 that way, and closer to 1/2 that way. We said there was vertical asymptotes at x equals 1. And yeah, that definitely looks like it approaches 1 that way, and then approaches 1 that way. But then we had another one at x equals negative 1.5, or negative 3/2. And you can see there, so two vertical asymptotes that it gets closer and closer towards. Let's also put in the y equals 1/2. There we go. And finally, we said there were no x-intercepts, right? So when I look at what's going on this way, it stays positive forever that way. When I look at this way, it stays positive forever this way. Clearly, this graph increases and then decreases again. So yeah, there are no x-intercepts. It doesn't cross over. I can see that on my graph. You can zoom out a whole bunch and kind of tell that way as well too. All right, anyways, this is a little bit about what we're going to be getting into for this week, next week, and the following week when we deal with rational functions, their graphs, working with rational functions. Hope this is a good introduction. Let's go back to our PowerPoint. So to summarize what we did a lot with variation, direct, inverse, and joint variation. And then we just touched on a little bit about rational functions, what they are, looking at some graphs of hyperbolas, finding x and y intercepts, finding horizontal and vertical asymptotes, and starting to connect with this function and what it looks like on our actual graph. All right, let me know if you have any questions, and have a good time working on week 3 stuff.